As he said, I'm going to talk about some state-of-the-art adaptive variational quantum algorithms for quantum simulation. I've been told that I have people from multiple backgrounds, so I have some simple introductions to some relevant topics, and feel free to ask any questions at any time during the talk. And I will start with the most important question: why do we care? Why do we want to simulate quantum systems? Well, simulating strongly correlated quantum systems is important for applications, including but not limited to, for example, drug discovery and materials discovery and drug design. So we are interested in simulating these materials with applications in the real world. And why do we need quantum computers to do that? Let me motivate that with some examples of quantum systems and how much classical storage we need to represent them. So if we start with the simplest possible system, that's one qubit, so just a single qubit. And how much classical memory do we need to represent the corresponding state? Just 32 bytes. How to store this? Well, you can just write it down in your notebook. So you don't need any significant storage capacity to do this. Now we move on to a 10 qubit system. How much memory do we need to represent it? 16 kilobytes. Can you write it down? Probably, but hopefully you have better things to do. But it does still fit in a standard CPU cache, so it's pretty light memory. We move on to 30 qubits. We now need 16 gigabytes. It no longer fits in the cache, but it does fit in your laptop RAM. So it's still pretty easy to store the system. Things change at 46 qubits. We now require 1 petabyte, and we need a middle-sized data center to store the full state. We go to 100 qubits, and it requires 10 to the 31 bytes. You know, things are really bad when it no longer has a name. And this exceeds all storage on Earth. So even if you were wanted to distribute the memory to all possible devices, classical computers that you find on Earth, you wouldn't be able to store the state, and not by a small amount either. So what do we mean simulate a quantum system? Usually we're interested in solving the Schrödinger equation for the particular system that we have. And this is an eigenvalue equation. So we are given the Hamiltonian that describes our system, and we want to find the eigenvalues and the eigenstates of this Hamiltonian. And usually we care particularly about the ground state. This is the most, or at least the first thing that we usually do. So I will be focusing on the ground state throughout the talk, although the methods that I will speak about generalize to other excited states as well by, for example, imposing orthogonality constraints. Now, a fundamental principle to solve the Schrödinger equation is the variational principle, which tells us that the energy meaning the expectation value of the Hamiltonian in any normalized state is lower bounded by the ground state energy. So this transforms the problem into a minimization problem. We try to find the state that minimizes the energy, and this will be the ground state if we successfully perform this minimization.
Mafalda, can I bother you about, I'll call it a stupid question, just go back to your previous slides. So I've seen people say this before, but this is not quite true, right? So let me just ask you, how are you doing your math here? Because a lot of people will say, okay, you have 2 to the 100 states, but also in classical computing, you have 2 to the 100. It's just that then we take the log and then we get bits to bytes. So what is your math for this?
I'm just assuming that we're storing the full state vector using like a float to store each of the episodes.
So you're assuming a float for everything.
Yeah. So it's just a rough estimate. I mean, technically, if we wanted to start full envelopes, we would need infinite precision, but that also doesn't make sense. Of course, like in some cases, we need far less if we have a stabilizer state, right? And, yeah.
Right. Yeah. And then many people would say, okay, many of us, we readily do 30 qubits, we do orbitals. If we say a qubit is an orbital, we do hundreds of thousands of orbitals just so we don't store the whole state. Blah, blah, blah.
Yeah.
Fair enough.
So in particular for the systems that I'll be focusing on are molecular systems, for which the Hamiltonian look like this. So we have 3 terms. We have the term associated with kinetic energy of the electrons, and then we have the potential from the electron nucleus and electron-electron interactions. So this is the type of Hamiltonian that we are dealing with. And we will typically write it in terms of fermionic ladder operators using the second quantization formalism. So just a quick introduction to these operators for people who might not be familiar with them. We have a creation operator that creates an electron in a mode I that's represented here as this circle, with the electron being the black ball. So the creation operator just creates an electron on an occupied orbital. What happens if the orbital is occupied? Well, it just quenches the state. This is just a reflection of the fact that it's impossible to add an operator to an orbital that already has an electron due to the Pauli exclusion principle. And the annihilation operator does the opposite. So if we have an occupied orbital, we remove an electron. If we have an unoccupied orbital, it just destroys the orbital. We can't have a negative occupation number. And the fermionic ladder operators obey the anti-relations relations here in this slide that result in very important properties for the fermionic wave function, such as anti-symmetry. Now, the question is, we have two quantum mechanical systems. We have the target, that's the molecular system, that's what we want to study. And this satisfies the Schrödinger equation, and we want to find its ground state. And then we have our resource, which is the quantum computer. So this is what we can actually manipulate, and this is what we can actually use to perform computation. But the ground state of the quantum computer is not the same as the state of the system we're targeting. So they're both quantum mechanical states, but they don't obey the same rules. So how do we represent states of the target system or a molecule on the quantum computer? So fermions and qubits have very different properties. Fermions are indistinguishable particles. So if we have a fermionic wave function and we exchange a pair of fermions, this has no observable effect on the wave function. There is one particularity though, which is if we exchange two fermions, we see a sign flip in the wave function. This doesn't change the observable properties, but it does affect the properties of fermions, such as resulting in the Pauli exclusion principle. So the fact that no two fermions can occupy the same fermionic mode. Qubits are distinguishable. So generally, we think of quantum circuits. We have different wires corresponding to different qubits, and we can apply a particular operation on a particular qubit. We can say this qubit in the chip is the one that I want to apply this rotation to, and the state is different depending on which qubit I apply the rotation to. So qubits don't obey any anti-symmetry principle because they are distinguishable. Doesn't even make sense to talk about anti-symmetry in this context, because if we exchange two qubits, the wave function is completely different. So one possibility for representing fermionic states in qubit states is the Zartan-Wigner mapping. And the essential idea is that we can map unoccupied orbitals to qubit states 0 and occupied orbitals to qubit states 1. So each orbital is mapped, each spin orbital is mapped to a qubit, and the occupation number is given by the state of the qubit in the computational basis. And this can be achieved by mapping the fermionic ladder operators very simply into this sum or difference of Paulis. This correctly results in the desirable properties for the ladder operators. So we have the correct action on the 0 and 1 states. For example, if we try to create a fermion on state 0, it changes to state 1. If we apply the creation operator on 1, it destroys the state. So everything works very well for a single orbital. So are we safe? In principle, we only need 0 or 1 occupation numbers. So we're dealing with a fermionic number, so we don't need fermionic system, so we don't need more dimensions. The question is, does this mapping satisfy the anti-commutation of the operators? Let's see one simple example. So we have two orbitals I and J, and we have fermions occupying, one fermion occupying each of these orbitals. We apply the annihilation operator on mode I, and this removes the fermion from this mode. And now we apply the same annihilation operator, but on mode J, and this removes the fermion as well. So now we go to a state that has no fermions. And now we do the same thing, but in reverse order. We apply the annihilation operator on J, we remove the fermion from this mode, and now we apply the same the operator on I. Sorry, this is and on I, and we get an empty system with no fermions. Now, the reversing the order of these operations resulted in exactly the same state. There was no point in which a minus sign was added to the wave function. Yet, we know from the anti-commutation relations that switching the order of these operations should result in a minus sign. So how can we correct this? Let's say we have a multimode fermionic system. So we can choose an ordering for the modes, and we will set the sign of a letter operator acting on a given mode based on the parity of the occupation numbers of all the modes that come before it in our order. So of course there will be many different arguments that we can take. We just choose one specific argument and we stick to it. So let's say, for example, we are interested in a letter operator acting on mode I. We count the total occupation of all the modes coming before I. If the parity is even, we choose the letter operators as I showed in the slide before. If the parity is odd, we flip the side of the operators. And of course, we can do this for any mode. So if we take mode J, we use the same parity-based sign setting, with the difference that we count the total occupation before mode J. So in this case, we include more fermionic orbitals in the parity calculation. So as a simple example, let's consider a 6-mode system. So we have here a 6-mode system with 4 fermions in some of the modes. Let's say we remove a fermion from mode 2. We represent this pictorially, but now we have to consider the sign. We count the total occupation number in modes before 2, so we see that this parity is odd, so we add a minus sign to the wave function. And now we do the same thing, but acting on fermionic mode 4. We count the parity. In this case, the parity is even, so we just keep the minus sign. We don't change the sign of the wave function. What happens if we do the reverse order? Let's start with the same system. We remove the fermion from mode 4. The sign will be negative because we have the odd parity leading up to mode 4, so we flip the sign. But now when we apply the destruction operator on mode 2, we get again an odd parity, so we get a minus sign. So as you can see, this obeys the fact that when we flip the order of the operations, we get a minus sign that's desired. And with a few more pen and paper calculations, you can convince yourselves that this actually works for all possible cases of the desired anti-commutation relations. So now we have, yes.
Sorry, what are the X and Y operators?
Yeah, so the X and Y operators are just Pauli operators that act on a specific way on the qubit state. But for now, you can just consider that these operators here you can consider their definitions to just be like this. So the operators work like this, and we just have a way of representing these things in terms of operators that act on qubits.
And that's a known way to, like, we know how to do that on qubits.
Yes, yes. So X and Y are very simple operations to apply.
They're just the standard Pauli heuristics that we learned in Mafalda. Yeah.
So how do we account for anti-commutation in a multimode system? We see that we need to include this parity factor. So now instead of mapping the letter operators to these operators, we instead want to map them to the same operators, but with a sign that depends on the parity of the fermionic modes before I. As you can imagine, this is not exactly an operation that can directly be implemented on a quantum computer. So how do we choose this? How do we perform this parity calculation in a way that is representable in a quantum computer? So recall that we are mapping the fermionic modes, occupied or unoccupied, into qubit states, 1 or 0. And we actually have one convenient operator that gives us precisely this parity. So we have the operator Z, that's the Pauli Z matrix, and acting on state 0 and 1, it results in the same state with a plus or minus sign attached. So when we take the product of Z's on all qubits up until I, we get exactly the parity of these modes. So the final formula for the transformation of letter operators is as shown in the right on this slide. This is exactly the transformation that we want, and this is the Jordan-Wigner mapping that gives us a way to map an expression written in terms of fermionic ladder operators into an expression in terms of qubit Pauli operators. Note that the operators that we constructed without the Z-string, so these operators here on the left are first attempt at representing the ladder operators, are often called the qubit ladder operators because they perform the same action on the qubits up to the anti-computation relations that are characteristic of fermions. Now that we're done with this background part, here's a brief outline of the topics that I will discuss in terms of the algorithms. So I'll start with the variational quantum eigensolver. I will follow with an adaptive version of this algorithm, and then I'll talk about my contributions. This is a particular operator pool for ADAPT-VQE called the couple exchange operator pool. Hessian recycling, that's a strategy to streamline optimization, and a co-design version of ADAPT-VQE that tailors the algorithm to a particular architecture. And finally, I will talk about sample-based quantum diagonalization and some hardware experiments that we did. So starting with a quick introduction to quantum circuits. In the circuit model of quantum computing, we represent qubits as wires. So each wire represents a qubit. Operations on a wire represent operations on the corresponding qubit. We have single qubit rotations that can be applied to each qubit. They are often parameterized, so we can choose a parameter, and this parameter is then implemented on architecture to some fixed precision. And then we have entangling gates. One popular type of entangling gates is CNOTs, but there are many others, and they have variable representations. Usually they act on 2 qubits, but there can also be operators acting on more than 2 qubits. Now, we need gates to perform operations on the quantum computer, but gates also result in the accumulation of noise. So typically, 2 qubit gates are associated with higher errors than single qubit gates because they need multiple qubits to interact and usually also take longer to implement. So for example, taking a recent generation IBM device, Heron R2, the Boston machine, we see that 2 qubit gates have a median error about an order of magnitude higher than single qubit gates. It's 10 to the minus 3 versus 10 to the minus 4. So one metric that's often taken to evaluate the noise resilience of a circuit or an algorithm is the CNOT count. And this is what I'll be mostly using for the rest of the talk. So finally, we get to the variational eigensolver, or VQE for short. This is a hybrid algorithm where we use both a quantum computer and a classical computer. So we use the quantum computer to prepare trial states, and we use the classical computer to evaluate to update the parameters and minimize the energy. So this is basically an optimization where the cost function is evaluated using a quantum computer. The quantum computer only prepares states, measures energy in these states. As we discussed before, we can represent and measure fermionic states using the quantum computer. What does the circuit actually look like? To be able to prepare states on the quantum computer, we need to choose a particular circuit structure for the parameters to then be optimized and lead us to the ground state. The first idea, and most popular initially, was to use this hardware efficient ansatz that consists of gates that are particularly convenient to implement on our target computer. So let's say we have a particular quantum computer. It has some available gates between certain pairs of qubits. It has some available rotations that we can natively implement. So we just throw this in a circuit that's convenient and doesn't require any further processing. And we run, we optimize the parameters, and we try to reach the ground state. So this is very easy to implement. It doesn't require any sort of translation. It uses native gates. It does have a major downside, though. It was shortly after proven that this type of circuit structure leads to variant plateaus. This is an issue where we observe that the gradients of the cost function vanish exponentially on the size of the system, which means that we can't actually train the circuit. So we need the cost of training the circuit and obtaining the solution is exponential with the system size, meaning that it quickly becomes intractable to optimize the parameters. And following this, there were many strategies to mitigate the problem. So there were several strategies, such as initialization techniques, or keeping circuits shallow, or reducing the locality of the observables that were shown to improve the trainability. So it softens the exponential decrease of the cost function. But more recently, there was a paper that show that this type of restrictions limit the expressibility of the circuit in such a way that it actually opens the door to dequantization. So it opens the door to strategies to classically simulate the circuit, leading us to not need this hybrid quantum classical feedback loop, meaning that we can actually obtain advantage from these circuits as compared to classical methods. What is the solution for VQE then? Well, one strong option is to use problem-tailored circuits. So, for example, we have the unitary coupled cluster signals and double ansatz, also called UCCSD. And this circuit is inspired by classical methods for computational quantum chemistry. So the ansatz looks like a unitary that's generated by single and double fermionic excitations acting on the Hartree-Fock state. That's the mean field solution, just a simple solution that we can obtain classically, and that can be represented as a computational data state in the quantum computer. So using the Jordan-Wigner mapping that we discussed, we can translate these excitations into Pauli operators, and then we can implement the circuit. Are there any downsides to this method? Yes. Let's look at this example Hamiltonian for a simple system. We have all of these terms in the Hamiltonian. Each of the terms maps to several Pauli streams, as we saw, using the Jordan-Wigner transform. And to implement the UCCSD ansatz, we need to implement the exponential of each term once or more. We might actually need several implementations of each term. And this is the case of a 4-qubit Hamiltonian for a very simple molecule. So as the molecule size grows, we'll need more and more operators to implement the ansatz. And this means bigger circuits, which, as we discussed before, leads to a greater accumulation of noise and less output signal. Can we do better than this? Yes. So this is the idea behind the ADAPT-VQE algorithm that was proposed by a team at Virginia Tech a few years ago. So in this strategy, instead of having a fixed circuit of excitations, we start with an empty circuit, and then we add the excitations that are more relevant for the system. The selection criterion is the gradient. So the gradient is the local energy change, and we hope that operators with a high local energy change will also have a high impact on the energy once a full optimization is performed. So how does VQE proceed? We start with an empty circuit representing a very simple classical state. And we measure the gradients of all operators in our pool of candidate operators. So the operator with the highest gradient is selected and added to the ansatz with its own variational parameter. We optimize the variational parameter, we measure the gradients again, and we add again the operator with the highest gradient. That's another operator. We add another variational parameter to it. We re-optimize both parameters, so each time we perform a full optimization, and then we repeat the procedure multiple times until we have a full circuit of operators. The stopping criterion can be, for example, the total norm of the gradient vector falling below a given threshold. Yes.
Do you choose some initial state, or is there any guidelines to choose?
Yes, it's usually the Hartree-Fock state. But anything with correct particle number should in principle be good.
Okay.
So for UCCSD ansatz, we have to evaluate the exponential of the cluster operator. So if you don't have a disentangled method, for example, ADAPT, how does one evaluate that kind of ansatz on a quantum computer?
So how do you implement the So if you just have this type of ansatz using the Jordan-Wigner transform, this translates to a linear combination of Paulis. The exponentials can be implemented in the quantum computer using ladders of CNOT gates to calculate the parity, and then rotations and another ladder of CNOT gates. So for example, to implement XXXY, you need 6 CNOTs and 1 rotation. So there's a way to compile this into a quantum circuit. The main problem is that the operators in the generator don't actually commute. So you need to implement a method like throttlization. So this implies implementing operators multiple times with a fraction of the total time in the parameters.
But does it naturally truncate? Because the problem in classical UCCSD is that it never truncates.
Yeah, so the series doesn't truncate, but implementing the operator with throtter step 1, for example, is possible.
Okay.
But this is kind of an approximation to the ansatz. The hope is also that since the UCCSD ansatz is variational, we can try to truncate the throtter implementation and just optimize the parameters and have hope that that absorbs some of the.
Okay, thank you.
Yes.
So usually how large, how many operators do you have?
In the UCCFD ansatz, it goes with the fourth power of the number of spin orbitals.
Okay.
That's equivalent to the qubit count. Yeah. So how the algorithm that I described about VQE, it needs both to measure energies in the quantum computer and gradients for the operator selection. So how do we measure these things? To evaluate the energy, we map the expectation value, or we map the Hamiltonian using the Jordan-Wigner transform to linear combination of Paulis. And then Pauli operators can be measured in a straightforward way in the quantum computer. We just apply a circuit at the a portion at the end of the circuit with some extra gates, and we measure on the computational basis. It's just a standard task for a quantum computer to do. The gradients of the operators, they can actually be written as an expectation value as well, because they're always put at the end of the circuit. And this expectation value is just of the commutator of the Hamiltonian with the generator of the corresponding operator. So this allows us to measure the gradients in a very similar way that we measure the energy, because this commutator maps to a linear combination of Pauli strings in itself. Yes.
So this is in essence like an analytic gradient, right? The gradient's not the cost of measuring a gradient is essentially the same as measuring the energy, or is there a cost scaling with the system size for the gradient? Like that is independent of energy or larger?
Yeah, it's the cost to evaluate one gradient is similar. We do have multiple gradients to evaluate, while we only have one energy to evaluate. But in terms of how much is actually required, it depends a lot on the precision, because the precision that we need to evaluate the energy might not be the same precision that we need to evaluate the gradients. So for example, at the start of the optimization, we actually need lower precision in the gradients because gradients are high. But as we converge toward ground state, gradients become smaller, so we need a higher precision to measure them.
Okay. And I guess you're getting the estimate by sampling one entire, like you can sample all directions at once, or you're sampling each one individually?
So
For computer screen.
in terms of the pool operators, like if we want to measure all the pool operators, we're not exactly sampling individually, because what happens in practice is we have a lot of commutators of this style, like one per candidate operator, and these translate to Pauli strings. But actually many of these Pauli strings commute with each other, so we can group them all and measure them using the same quantum circuit to save measurements. So we don't measure them all at once, but we do measure many of them at once to save measurements. So our goal will be to produce bond association plots. This is a standard technique to benchmark state preparation algorithms, where we find the ground state for multiple bond lengths, and we'll simulate ADAPT-VQE for a bunch of these bond lengths to compare the resulting bond association plot with the exact solution, which we can get for small systems, just using classical methods that don't scale but are good for toy problems for us to compare against. Chemical applications require very high precision, so this type of curves, as plotted here, of the ground state energy in a linear scale, usually makes it hard to actually see if the algorithm is working or not for experimental purposes. So we typically plot the error in a logarithmic scale that is more sensitive to small changes. And what I will be plotting throughout the talk will mostly be like this, so errors in a log scale, but it represents this type of bond association curves that test the algorithm for multiple correlation, degrees of correlation. So let's see how the algorithm performs using classical simulations. First, on the left, I have a plot of the error versus the bond distance for a molecule composed of 6 hydrogens. This is a 12-qubit molecule. So we have the Hartree-Fock state in green. That's a solid curve. This is just a basic classical approximation. And then we have the UCCSD ansatz as the solid orange curve. And we see that about half of the UCCSD points are within the blue region. This is the region of chemical accuracy. That's our target for experimental applications. But as the bond distance becomes more stretched, UCCSD is no longer able to converge to chemical accuracy. The ADAPT-VQE curves are the dotted curves. So we have three noted curves that correspond to different convergence criteria. So as the convergence criteria becomes tighter, the error becomes lower. So we let the algorithm run for longer. In the case of the highest threshold, we have a very similar result to UCCSD. One step further, and the ADAPT-VQE results get better, so the circuits are deeper, so they result in better energies. And at the highest threshold, we obtain chemically accurate solutions across the whole bond association curve for hydrogen.
Sorry, real quick, is this the bond distance between each atom in the bond?
Yes.
Okay, thank you.
And is this just a diatomic or is this like a linear chain of
It's a linear chain
Okay.
of 6 hydrogroups.
Also, how is ADAPT able to do better than UCCSD even though it has like lesser number of operators?
Yeah, so first, it usually does have fewer operators, but it can grow the ansatz even beyond UCSD. So when we pick an operator from the pool, we don't remove it from the pool, it still stays there, so you can add each excitation multiple times.
Okay.
But the thing is also that it does select the most important operators for the ansatz. So often when we have UCCSD, we have some parameters and operators that are irrelevant. So they're in the circuit, but they're not really doing anything. And ADAPT does select operators that are doing something for the cost function. The ordering of the operators is also important. So we're ordering the operators in such a way that the place they are at has the maximum impact on the cost. So it's an improved ordering with respect to UCCSD. So if we were to organize excitations using UCCSD, we also could obtain a better energy. And on the right, I have a comparison of ADAPT with other operator ordering strategies. So we have the error versus the number of parameters or excitations in the ansatz. And we compare ADAPT-VQE, which is the purple curve, with random or lexical ordering. And you see that it converges much faster when we use ADAPT, which means that the gradient-informed selection criterion is significantly better than random or lexical operator ordering.
Wait, what are you comparing it against? What is random lexical?
So random is just selecting random excitations.
Okay.
So at each point you select a random excitation and then you keep appending them. And lexical, you order them by excitation numbers. So for example, you start with excitations involving orbital 0 and 1, then you go to higher excitation numbers. Yeah. So one important element of ADAPT-VQE is the operator pool, these candidate operators that we choose to add to the circuit. The original option, as I'm motivated based on UCCSD, was to use fermionic excitation operators. So the operators look like this with some linear combinations of products of fermionic ladder operators. This does have the downside that we usually have, so the Jordan-Wigner Z-string that I talked about that implements anti-commutation, it acts on average on a linear number of fermionic modes. So it acts on all, for a given mode, it acts on all modes before it. So on average, it will act on half of the system. This means that we will need many 2-qubit gates to implement them in practice. So an option that's a bit more hardware efficient are qubit excitation pools that are the same, but we replace the ladder operators with a qubit version that doesn't have this Jordan-Wigner Z-string. And it's easier to implement. And we can go one step further and just use individual Pauli strings. So we can map any of the expressions before to Pauli strings, and we can just choose each specific Pauli string to be an option to include in our pool. How do these pools compare? I'll start with a comparison of qubit and fermionic excitations. So we have a plot of the error versus the number of qubit or fermionic evolutions. Qubit evolutions are in blue and fermionic versions are in red, and we see that the convergence is very similar. So removing the Z-string from the operators doesn't significantly affect how many operators we need to reach a given error. And now, considering a plot of the error against the number of CNOTs in the ansatz, we see that the fermionic version of the algorithm, which is the red curve, is the one requiring the most CNOTs. followed by the qubit pool, and finally the qubit excitation pool is the most hardware efficient one, requiring the fewest CNOTs to reach a given error. This means that the qubit excitation pool is the most convenient to implement in devices and the most viable in the near term because it will accumulate fewer errors. So our recent proposal was this pool consisting of coupled exchange operators. Let's motivate this with an example of a set of 4 orbitals. So we have 2 spatial orbitals, each of them has a spin down and a spin up spin orbital. And let's say that we have orbital P that occupied with 2 electrons. One possible valid excitation is exchanging electrons from the orbitals P to the orbitals Q. So this preserves the number of fermions, and it also preserves the number of up and down fermions, which are desirable properties. But considering the same set of excitations, we also have another valid excitation that moves 2 electrons from orbitals P up, P down, and Q up to P up and Q down. So this is also a valid excitation. The interesting part is that these 2 excitations map to a linear combination of the same polystrings. And if you use particularly well-constructed circuit structures, you can leverage this to implement algorithms using fewer gates than you need to implement if you didn't consider this linear combination. What does that look like in practice? Here I have an example of the error versus the CNOT count for the pools that I mentioned before and our new operator pool. So we see that the new operator pool, that's the CEO pool in blue, requires less than half the CNOT count of the previous best performing pools that are the qubit excitation pool in red and the qubit pool in green. So this means that we can reach the same error with shallower circuits that are easier to implement on noisy devices. Another strategy that we proposed recently was hasten recycling. This is a strategy to improve the optimization process of ADAPT-VQE. So basically, in ADAPT-VQE, as I described, we perform multiple optimizations, one per iteration. Hasten recycling is a way of saving information concerning the second derivatives of the cost function from one optimization to the other. Basically, we recognize that these optimizations have relevant information for each other. So instead of fresh starting the optimization of the algorithm in each iteration, we save some of the information. And this allows us to save on the measurement costs to reach a given error. For example, I have here for hydrogen molecule a plot of the number of function evaluations per ADAPT-VQE iteration. And we see that with hasten recycling, the blue curve, we need significantly less energy evaluations. This means that we need fewer calls to the quantum computer, which means lower costs. And the error obtained by both methods is exactly the same, so they actually create the same ansatz. So we're just saving on the measurements without any downside. This is just a small technique on the optimization part. Finally, I have a couple of other improvements that were proposed by other graduate students in the group. We have the Tetris adapt variant, where we favor operators that act on disjoint qubits to avoid these gaps where qubits are idle and create a shallower circuit that is more noise resilient. And another strategy related to the question about the measurements is to group many of these operators, for example, the CEO pool or the qubit excitation pool, into commuting groups to minimize the number of measurements that we need to evaluate the gradients. And we can combine all of these to create a state-of-the-art version of the algorithm. So we combine the CEO pool, hasten recycling, the Tetris protocol, and the gradient measurement protocol to create this blue curve that represents the state-of-the-art of ADAPT-VQE and compare to the original algorithm in orange. The plot shows the error against the CNOT count, again as a metric of noise resilience. And we also include the UCCS, the ansatz, the pink diamond for reference. So we see that we require 90% fewer CNOTs as compared to the original algorithm, and we also have improvements in other counts, such as CNOT depth or measurement cost. Now, how does the current version of the algorithm compare with other ansatz for VQE? So ansatz is a state proportion circuit. we are comparing variants of ADAPT-VQE, but we can also have some circuits that are not adaptive. So we can have some circuit structure that is informed by chemistry or otherwise, and we can optimize these circuits as well and compare them to ADAPT-VQE. So here I have a few examples of a few of these techniques. The plot shows the error versus the CNOT count in the circuit. We again include UCCSD VQE for reference, but also some more sophisticated methods for safe preparation. We include in purple the spin-preserving version of unitary coupled cluster singles and doubles, and then we include some gate fabrics that are based on preservation of fermionic quantities, so that the quantum number preserving gate fabric and the tau unitary product set fabric in its several varieties. So the algorithms that do converge are the QNP and the UPS. So these are number preserving gate fabrics, and they converge to chemical accuracy. The spin preserving version of UCCSD does not, nor do other ansatz that are not included in this slide, such as the hardware efficient ansatz, as I showed before. This ansatz is very hard to train, so it doesn't usually reach chemical accuracy. As far as this go, they reach chemical accuracy at a slightly lower CNOT count as compared to ADAPT-VQE, but still within the same order of magnitude. Where things change a lot is the measurement cost. So in the plot that we compare the measurement cost, we see that ADAPT-VQE requires 5 orders of magnitude fewer measurements than any of the other alternatives that reach chemical accuracy. You might be wondering why. So the reason is that this parameter recycling strategy for ADAPT-VQE results in a warm start of the optimization that helps us to converge to a minimum without suffering from any trainability problems. The other ansatz, they start with a full circuit, and we need to perform a parameter optimization, but the parameter landscape is very complicated and usually full of local minima, shallow local minima. So to find a good minimum, we usually need to random start the optimization and run it many times. And for these 12-qubit molecules, we're already talking about thousands of optimization that require many measurements to converge repeatedly towards the nearest minimum and follow until we find a good solution, in this case, a chemically accurate solution. So 5 orders of magnitude different in measurement cost means that these other ansatz are likely not valuable, as they can represent a completely prohibitive amount of time obtaining measurements on the quantum computer. Finally, I want to talk a bit about the transpilation overhead. So I have been assuming before, the truth is common in quantum algorithms literature, that we can implement interactions between any pair of qubits. So this corresponds to a fully connected graph, where we can implement entangling gates directly between each two qubit pair. But in practice, we often have limited connectivity. So we might have, for example, that each qubit is only connected to 2 neighbors. So in this case, we can directly implement, for example, an entangling gate between qubit 0 and 2, because they are not connected in the graph of the processor. So this means that the interactions are not natively implementable on hardware. Naively, we can just run any algorithm, create any circuit for any algorithm, and then transpile it to the target architecture. There are multiple techniques to do that, but they do result in an overhead in terms of the gate counts. So here I have a comparison of the error versus the CNOT count in all-to-all connectivity on the left and linear connectivity on the right for ADAPT-VQE with the same 3 operator pools that we discussed before. So all the pools, the relative behavior of the pools is roughly the same, but all the pools have an overhead of roughly 4 times more CNOTs when transpiled to linear connectivity. So this means that it will be harder to implement on hardware because noise will accumulate more when we have more gates. Can we do better? Yes, we can. There are a few strategies that we can implement to optimize the transpilation process and decrease this overhead. How does transpilation usually work? One very useful gate is the swap gate that exchanges qubits. So this can be implemented using 3 CNOTs. And what it does is it changes which physical qubit represents which qubit in our circuit. So for example, let's say in the previous case, you had qubit 0 and 2 were not connected, but you could swap qubit 2 with qubit 1 and then implement an interaction between those two, which in practice is an interaction between qubits 0 and 2. We just changed which physical qubit represents the state of this qubit. So for routing, we usually use swap gates followed by the operation that we want to implement, followed by possibly swap gates to undo the exchange of the qubits. We also have another interesting gate that's the fermionic version of this swap gate that essentially exchanges fermionic modes instead of qubits. So it has an additional sign that accounts for the sort of anti-symmetry of the exchange. So this gate can be represented similarly to the swap gate for visualization, but it requires fewer CNOTs to be implemented than the regular swap gate. So it requires only 2 CNOT gates instead of 3, so it's more hardware efficient. To see how this can change things, let's look at 2 particular excitations. So we have a qubit excitation and a fermionic excitation, both between qubit 0 and 99. If we have alt-hoc connectivity, the qubit excitation is very simple to implement. It can actually be implemented using only 4 CNOTs. So it's very cheap operation to implement on hardware. The fermionic excitation requires 400 CNOTs, roughly. This is because of the Jordan-Wigner T-strings that require many gates to be implemented on the quantum computer. What happens if we move to linear architecture? Well, now the qubit excitations require 600 CNOTs to be implemented. We need a lot of swap gates to bring qubits 9 and 99 and 0 together to implement this excitation. How about the fermionic excitation? Surprisingly, it requires the same number of CNOTs as before. This is because the fermionic excitation was already acting on a higher number of qubits, and we can actually perform the exchange more efficiently if we use fermionic swap gates as compared to regular swap gates, because they require fewer CNOT gates to be implemented. One other thing that we can do is modify the selection criterion of ADAPT-VQE to favor the hardware efficiency. So the original selection criterion is aiming the operator that produces the greatest local energy change, so the operator with highest gradient. But different operators have different costs on hardware. So some operators are easier to implement, and some operators are harder to implement. And we can factor this into the selection criterion by dividing the gradient by a hardware motivated penalty. So we can use, for example, the number of CNOTs in a linear connectivity or another target connectivity, to represent the fact that we want to favor operators that have lower costs on hardware. So we want to favor those operators that are very easy to implement and that are less noisy. And here is an example of the result of running this algorithm, this co-designed version of ADAPT-VQE on hardware. So we have a plot of the error versus the CNOT count in the circuit. The red curve corresponds to regular ADAPT-VQE in alt-wall connectivity. And then we transpile these same circuits to linear connectivity. That's the green curve. And the blue curve corresponds to the co-designed version of ADAPT-VQE in restricted connectivity as well, so also linear connectivity. So not only does the co-design process improve the CNOT count roughly 10 times with respect to the original transpiled circuits, it even reduces the CNOT count with respect to the original ADAPT-VQE without any connectivity restrictions. So this is an example of the importance of co-designing the state proportion circuits, taking into account the target hardware. Finally, I want to briefly introduce a method that we implemented on hardware recently. This is called sample-based quantum diagonalization, or SQD, also known in the literature as quantum selected configuration interaction, or QSCI. So the idea is we have this big matrix. So we have the big exponentially big Hamiltonian matrix. And ideally, we would want to diagonalize it to obtain the eigenvalues and eigenstates. These would be the solutions to the Schrödinger equation. But performing diagonalization on an exponentially big matrix is hard. It's not something that we can do for bigger systems, even if we try to use a supercomputer or some better processors. So if we can diagonalize the whole matrix, what do we want to do? We want to implement a diagonalization strategy, but we can do it on the full matrix. The idea of a sample-based quantum diagonalization is to use a quantum computer, but not to create a variational optimization loop. We use the quantum computer to give us samples that tells us which parts of the Hamiltonian are important. So it just selects some particular rows and columns of the Hamiltonian. given by samples obtained from the quantum computer, and we use these rows and columns to create a smaller matrix. And this smaller matrix can be diagonalized classically. So the quantum computer is only basically selecting the subspace in which you will project and diagonalize the Hamiltonian. And I will showcase a few examples for the task of ATP hydrolysis. So this is an important reaction. Breaking ATP down into ADP is a fundamental source of energy for cells. So this reaction is very important in biology with multiple applications from studying it. And the whole system is to simulate on quantum computers. So we break it down into fragments. And the study of the system was actually worked for the Q4 Bio program by Quantum Leap, a collaboration from a national lab by Stanford, collaboration with Virginia Tech, Brown, MSU, and NASA Ames, with Brenda's group doing a lot of work for it. And we implemented for SQD for some ATP fragments. So we have here in a plot of the energy versus the adapt iteration count. The blue points correspond to the standard SQD. So the algorithm that I described before, we use the quantum computer to set a diagonalization subspace for a diagonalization that is performed classically. And you see that as the number of adapt iterations proceeds, we get sometimes lower values of the energy, so better, but we also get sometimes some increases in the energy. This is because while the bigger circuit technically, ideally should produce better solutions, we have noise, and as the circuit becomes deeper, the noise also affects the output more, meaning that sometimes the samples we get from the quantum computer are less useful than they would be for a shallower circuit. How can we mitigate this? Well, this method called ADAPT-VQE that was developed by collaborator Ryan LaRose at MSU the idea is instead of using the output from each adapt iteration to run SQD, so using the samples from each iteration, we use the samples from all the adaptive iterations up to a given point. So we accumulate all of the bit strings that we obtain from the quantum computer, and we will diagonalize the Hamiltonian in the subspace that's dictated by all the bit strings obtained so far. So this results in the orange curve that, as you can see, converges much more smoothly. So we get this smooth desirable convergence, and the final point, the largest adaptive iteration we ran, is actually the iteration corresponding to the lowest error. This was done on a 24-qubit noisy simulator. Now let's see some results on hardware. We ran the SQD algorithm on IBM's Boston chip. This is 133 qubits, although we only used 64 of each for a 64-qubit ATP fragment. And on the right, you can see the connectivity map of the processor. So as you can see, it's pretty close to linear connectivity. Some of the qubits do have 3 neighbors instead of just 2, but most of the qubits just have 2 neighbors, as we would have in a linear graph. So we choose 64 qubits out of these. We created ADAPT circuits and we run them on hardware. We perform the diagonalization and we obtain these results. So here we have the Hartree-Fock solution, the basic solution, and the CCSD energy as a classical benchmark. And we have the SQD result in blue and the adaptive version in orange. And we see that the ADAPT SQD converges to a solution that's pretty close to the CCSD energy, with both of them performing significantly better than the SQD state. While the original SQD stopped improving the value after 5 iterations, the adaptive version continued improving the energy until we get to the final iteration number, corresponding to 40 adapt iterations. So to conclude, variational methods are a popular solution for solving the Schrödinger equation. There are many classical variational methods, but there are some wave functions that we can't represent efficiently classically. So quantum computers might be able to give us some advantage in representing states that we couldn't otherwise implement in variational methods. ADAPT-VQE in particular produces problem-tailored and compact circuits. This is more noise resilience, and it also enjoys some convenient properties for the ease of optimization. We obtained ground state energies for systems up to 64 qubits using SQD on hardware. And while I focus on molecular systems, there are many other realms of application. So the group at Virginia Tech has applied ADAPT-VQE to things like condensed matter problems, time periodic systems, thermal systems, and thermal state preparation, and combinatorial optimization, and more. So if you are interested in these applications, you should check out the work from other people at Virginia Tech. And that's it. I'm happy to take any questions.
Bye.